This is chemical equilibrium and Gibbs free energy part 2. And here I'm going to relate equilibria for simple reactions. Let's give the general case of reactants A and B turning into products C and D. And earlier I had talked about a chemical quotient, which is a useful value in these considerations. This is not the equilibrium constant unless these values are true at equilibrium. This is a quotient which describes at any particular time what the product of the concentration of the products divided by the product of the concentration of the reactants is. So we want to relate reversible reactions, and we want to relate so at equilibrium, let me write this, at equilibrium K EQ is equal to this value Q, not at other times, only. We're interested in understanding how to describe not the reversibility, but what determines the balance of this, what determines what the KEQ is in terms of energy, and specifically Gibbs free energy, which is the energy available to work. This is energy, Gibbs free energy is at constant pressure and temperature, and that's largely true in biological systems, so we tend to use it, and it's very useful. So we have an expression that is that the free energy change of a reaction, in this case from A plus B to C plus D, is equal to the standard, the value Gibbs free energy change at standard conditions, 1 molar concentration, plus a factor that depends on the concentration of the components. So what this is telling us is that, yes, there's a reaction at which we look at it under standard conditions, and it goes to it's favorable or not favorable because a negative value, right? If the change in free energy is less than 0, that reaction we say is spontaneous. Spontaneous not in the sense that it might suddenly happen, but that it can suddenly happen, that it's favorable to occur. So a free energy change that's negative value is spontaneous, meaning it doesn't need any energy to occur. Doesn't mean it does occur, because, for example, diamond can turn into graphite spontaneously, but it doesn't happen very often or very fast, very, very, very slowly. So we can describe Gibbs free energy as the way to understand whether a reaction is going to occur, and we can find this value. We can have it in a table. We can look it up in a table, and that's known for this reaction at standard conditions. But if the reaction is not in standard concentrations, then the likelihood it will happen depends. Earlier, the example was with alpha and beta glucose, and the reaction shown here is such that at equilibrium we will see a 36 to 64 ratio of beta to alpha anomer. If we look at standard conditions, so the question is, if it's at equilibrium, nothing happens, but if we alter those concentrations such that it's more alpha than beta, then the reaction will be spontaneous and delta G will be less than 0. So this is the way to understand that. So let's go through a couple process, a little bit of math here. So we can let's now look at equilibrium. So at equilibrium, so first we have a way to determine what the delta G naught is of any reaction by allowing a reaction to come to equilibrium. And if the reaction is at equilibrium, then delta G of the reaction is equal to 0. If delta G is equal to 0, then we can move this around, so we can say that the standard free energy change of this reaction is equal to negative RT ln Q, where R is the gas constant, and the gas constant in this case we're going to use joules. The value is 0.008315. Let me check if I didn't make a mistake there, because that value is going to be important for us. I think I'm correct. And T is the temperature in Kelvin. And typically we're going to be looking at something that's 300 Kelvin or something like that. So what can we do? We can allow a reaction to go to equilibrium, and then at equilibrium Q is also equal to KEQ, so that means that the standard energy, Gibbs free energy change of this reaction is going to be ln KEQ. So we can solve that then for this number, for the standard. So what does this tell us? It tells us that all these reactions would have a different value of Gibbs free energy at standard conditions, and we can determine that what that is by experiment, where we allow a reaction to come to equilibrium to find out what the equilibrium constant is, and we can then calculate it. So let's say minus 0.008315 times 300 Kelvin times the natural log of 64 divided by 36. So I have to get my calculator. Okay, I brought up the calculator, and I forgot to say the units of R here are excuse me. Excuse me, if I have the calculator showing it wants to go on top and I start writing and things are difficult. So the value of R here, this I wrote it in kilojoules per mole, so per mole Kelvin. So the other value of R is 8.315 joule per mole per degree. Okay, so we can enter this value in. If we enter this value in, we will find that the standard free energy for the change of alpha to beta glucose is about negative 1.44 kilojoule per mole. That's not a large value. That's quite small, but nonetheless, it's not surprising. It's merely an equatorial to an axial change. It's not a bond. It's not even a hydrogen bond here. So what can we do with this? We can use this value, put it in a table, and we can use it later. So first, just now we've seen that we can use an equilibrium constant to calculate the standard change of the reaction, and then we can go back and say, well, what if we have a reaction that is a solution that is 10% alpha and 90% beta? So 90% beta. What would be then, what is the change, what is the value of delta G? Will that be positive or negative? Which way will it go? So we can do that. We can calculate that delta G to be equal to the value of at standard conditions plus RT ln Q. So what do we have here? Delta G is going to be equal to what we already know, negative 1.44 plus, in this case, I'm working in kilojoules, so I'm going to have to be careful with the units, times 300 Kelvin times the log of Q, which Q is now 90 to 1, so it's a log of 9. And if I put that into the calculator, I come up with a value that delta G of this case is equal to 4.04 kilojoules per mole. What does that mean? This means this is greater than 0. That means the reaction will not go from alpha to beta, it means the reaction will proceed from beta to alpha, and it will do so with this amount of free energy. So there's two things we see here. One is that if we set up the reaction from alpha to beta, although this is what we'd say a downhill reaction, at this concentration of beta, where there's normally it should be the difference in free energy is sufficient to keep this ratio. If we put more beta in there than 64%, then the reaction will not proceed in the forward direction. It will proceed in the opposite direction, because this is a positive value, and we will have beta will turn to alpha. It will go back from 90, so it will go from 90-10 back to 64-34, and we can see that from the sign. The other is that this is the amount of energy that's available to be harnessed from that. It's possible to extract energy from concentration gradients, and if this is the concentration of beta and alpha there, we can extract this amount of energy. It's not very much energy, but you see the idea. Likewise, if we want to take our solution that is normally at equilibrium and change it such that it goes to 90% beta, it's going to cost us this amount of energy to do so. And that's the end of part 2.